Hi, my name is Alexandre Drouin, and I'm a PhD student at Laval University. This short video will present our NIPS 2017 paper on maximum margin interval trees. This is joint work with Toby Hocking of the McGill University Genome Center and François Laviolette, who is my PhD supervisor at Laval University. So in this paper, we propose a nonlinear algorithm for interval regression. Interval regression is quite similar to real-valued regression. However, the output labels are intervals that indicate a range of acceptable values. So in this case, any prediction that is inside of the target interval is considered as accurate. Now, the loss function that we minimize to obtain models for this objective looks like this. We have two terms, which are hinge losses. If the prediction is inside of the interval, then both terms are worth 0 and there is no loss. However, if the prediction is below the interval's lower limit, we have this term that will be positive, and otherwise this term will be positive. So in practice, we consider two types of hinge losses, the linear hinge loss and the squared hinge loss, although our method would generalize to any convex hinge loss. When we look at those losses with respect to real intervals, we see that they look like this. So if we have an interval with two finite limits, then you have a loss anywhere outside of the interval and zero loss inside of the interval. And you could also have intervals with only a single finite limit. To give you a concrete example of how this could come up in practice, suppose that you're running a study where you're trying to predict the survival time of patients given some treatment, and that by the end of your study, some patients are still alive. All that you know is that they survived a certain amount of time, but you don't know how long. So you're actually in this setting where you have right-censored data. So to learn such models, we actually use a decision tree approach that is based on the very classical recursive partitioning approach. We actually try to minimize this cost function by recursive partitioning, which is just a variant, an empirical variant of the loss function that I just presented. However, we have included a epsilon hyperparameter, which is actually a margin hyperparameter with a regularization effect. So to skip over the details, we showed that we can train such trees by solving a series of convex minimization problems. And actually, each of those problems is a sum of hinge losses, which actually look like a convex piecewise linear or piecewise quadratic function. So our main contribution is a dynamic programming algorithm that can solve n of those problems in n log n time for the linear hinge loss, and we have demonstrated this in the paper, and in big O of n squared time for the squared hinge loss. However, even if the worst case complexity is big O of n squared for this type of loss, we actually demonstrated that empirically we observe n log n time for both losses. Now, to go quickly over the results, we have shown empirically that both algorithms run in big O of n log n time. We have shown that we are able to model nonlinear functions that are based on intervals, whereas some existing methods were not able to do it. And we have shown that we achieve very good, actually state-of-the-art prediction accuracies in practice on real and simulated data sets. If you have any questions or feedback, please come by our poster on December 4th at NIPS in Long Beach, California. Thank you.